Hello, everyone. Welcome to our Conversational AI Reading Group. Today, we are very excited to have a great speaker, Emmanouil Benetos from Queen Mary University of London, talking about machine learning paradigms for music and audio understanding. If you have any questions during the talk, please raise your hand or drop them in the chat and we will go through them. Without any further ado, the stage is all yours.
Thank you very much, and thank you also for the invitation to talk to the reading group. That's great. As Una mentioned, I am here to talk about machine learning paradigms for music and audio understanding, and just a bit of context about sort of where is this coming from. So I'm based at Queen Mary University of London. Within that, we have the Center for Digital Music, which is a center for research and innovation in both audio and music over the last 20 years or so. We are currently hosting a fairly large doctoral training center called AIM, or AI in Music, with I think maybe 75 students who are basically producing some of the work that you are about to see. But we also do some non-music work at the same time. So we have other groupings such as the Center for Intelligent Sensing, which is widely about research in machine learning and signal processing for any sensor data. That could be audio, acoustic sensors, could be visual sensors, could be other kinds of sensors. And some work was also carried out as part of the Alan Turing Institute, which is the UK's National Institute in AI and Data Science. So in this talk, I will firstly give an overview about what I mean about machine listening that maybe includes elements of speech, but goes maybe beyond that. And then we'll also go through the three core sections of today, is some of the methods we have been developing on understanding, making sense of sounds using limited data, on making use and proposing new multimodal learning methods for making sense of sounds, and finally, a bit on some of the work we are doing on self-supervision, large pre-training models for machine listening, plus some future directions. So just to give an overview of what I mean by machine listening. So I would define it as the ability of a machine to interpret and understand audio signals. So we can call it as audio understanding if you'd like. What kind of sounds do we have in mind here? So it does include speech, but also music. We can think about any nature sounds that might be outside, everyday sounds, domestic sounds too. You can think about car horns, door slamming. You can think about glasses breaking, for instance. And a lot of the research carried out in the group is towards the latter sort of grouping, maybe a bit less on speech. We are focusing on maybe some more specialized speech cases such as podcasts or audiobooks, but most of the work is indeed on music and sort of everyday general purpose sounds. And what kind of sort of knowledge is behind that? So a lot of the methods we have been using originated from, well, DSP, digital signal processing, and of course, nowadays more and more on machine learning, AI, but we also make quite a lot of use on methods that have some theoretical grounding on acoustics, whether that's room acoustics, whether that's musical acoustics, bioacoustics too, and also perception, auditory perception, music perception too, in order to make sense of all these kinds of different types of sounds. If we zoom in a bit on the music side of things, so this is related to the field of music information retrieval or music information research. And there's quite a few traditional, let's say, problems in the topic. There's a lot of activity in London, where I'm based for, and there's a lot of activity worldwide in the creative industry sector for having models and methods and tools that are able to make sense of musical audio. Maybe you have an audio recording, you want to identify a series of tags or moods, emotions, instruments, genre. You might have a multi-track mixture and different instruments, different voices. You might need to separate those voices. It's a bit of a hard problem because in music, the constituent sources, they are what we might be calling strongly correlated, both on time and frequency, maybe in opposition to speech. And music transcription, so to convert an audio recording into some form of music notation to understand the pitches, the timings on them, maybe some expression as well. Audio identification, think about it as Shazam or similar sort of tools that are able to identify a particular sort of version of an audio recording. But now with the advent of multimodal AI, we are seeing quite a few new applications coming in, whether that's about sort of music captioning, music Q&A, text-based audio retrieval, just to name but a few, and I will go through some of these later in my talk. Then if we move on to the other side of things, so we have also challenges in machine listening, and that sort of these encompass any kinds of sounds. We have in a general purpose audio scenario, we can have multiple overlapping sources. Some of these might be also strongly correlated, as I said before. Data scarcity is an issue compared to maybe NLP or computer vision, or even I would say speech itself. There's just less strongly annotated data. And when I say strongly annotated, I mean with some maybe class labels, whether this is about the class, the sound event identification, or temporal annotations as well, start and end time of the events, for example. This is important. Sometimes we don't really have that. Another challenge we have, particularly in music, I would say, but also in other cases like environmental sounds, is temporal dependencies, long-term temporal dependencies. Sometimes in music you have a motif, a segment being produced, but you might have a repetition of this happening, maybe even 1 minute later, 2 minutes later. Humans, both in terms of the composer or the performer or the audience side of things, we tend to understand that, to acknowledge that, to perceive that, but making machines sort of have these long-term memory is not always so easy. Then you have, of course, noise, distortions, other kinds of effects into play. And also you have unseen domains in the same way that in speech you might have low resource languages, low resource cultures. We have also low resource musical cultures, potentially. In the environmental sound domain, you might have animal species you might not have encountered before. You might have new acoustic areas, environments that you might not have seen before, and you want to adapt your systems to them. And that's always a challenge. So what is the sort of traditional way of dealing with these things is that you somehow assume, okay, let's say that we have a well strongly annotated, sufficiently large data set that might allow us to adopt a supervised approach. That's the ideal scenario. In that case, we might sort of extract a time frequency representation as input, could be a CFT spectrogram, could be a MEL spectrogram, something like that. Could be a raw waveform, maybe. And the sort of basic building blocks is typically you would have some sort of convolutional layers in the beginning. Hopefully you will do your feature extraction using them, followed by some sort of recurrent or maybe attention layers that you hope would be able to follow somehow to have some sort of temporal modeling or some sort of temporal expectation. This is the ideal scenario, but in practice, it's not really the case, exactly because we do have a data scarcity, we do have low resource domains. We cannot really rely on this more traditional, let's say, supervised learning paradigm, which has its limitations. And as part of our efforts to try to benchmark a bit, the area we did propose recently, the Marble benchmark. So this is a large benchmark for music audio understanding that sort of defined 18 tasks across 4 different levels of hierarchy. We had level tasks that about the score, about the music performance, about more low-level acoustics, and more high-level description like tagging, for instance. And we try to benchmark existing state-of-the-art models around this. And this is something that we have been using thus far in order to benchmark some of the methods that I will be presenting later today. So this is the current state of things. Current state is that we can no longer rely on sort of this sort of small to medium-sized models. We cannot longer assume that we would have access to clean, strongly annotated data with class IDs, with timestamps. And we might need to follow a different approach, especially as new applications come in that might involve also multimodal sort of models, that text, audio models, and so on. So the first sort of thing that we tried, that was maybe a couple of years ago, 3 years ago, was on trying to start using methods that can cope with, that can support limited data. And the first thing we did was on domain adaptation. So I can define this. It's not too dissimilar from transfer learning. I can define it as a subdiscipline of machine learning that would deal with scenarios in which a model, which is trained on a source domain, we can then make use of this model. We can maybe rapidly adopt it to support an unseen target domain. And one such approach that we did a few years ago in ICAS was to have an unsupervised domain adaptation approach. So you have your strongly supervised model this is trained on data from one domain. In our case here, we were working on acoustic data. We were trying to recognize acoustic scenes in different cities. We had some data that was collected throughout cities in Europe for identifying the environment of a city. That's a street, that's a park, that's a bus, that's a metro. And we wanted to see if these models could adapt to different acoustic environments. In our case, our target domain was recordings in Singapore, which is a completely different acoustic environment. And we were back then sort of able to use unsupervised domain adaptation methods that kept some of the sort of feature extractors in place with an adversarial setup. We're able to try to discriminate whether this recording comes from the original source domain or from the new target domain. We're trying to come up with a model that would be able to be both robust in the original source domain of European data, but also be able to recognize acoustic scenes in the unseen sort of domain of Singapore in this case. And the same kind of approach, we also try to apply this for music. In music, again, it's a sort of relatively data scarce domain, but we do have some amounts of data, maybe in sort of pop, rock, mainstream Western musical styles. But that's not the only sort of source of music that we have. In our case, we had some unseen domain, in this case, that was Swedish traditional folk music. That was basically just a violin with a foot tapping. And again, using a similar sort of adversarial approach, we were able to differentiate between the more mainstream sort of Western sort of domain with a more traditional sort of folk music domains in order to support our task, which in this case was harmonic percussive source suppression, trying to separate the violin source from the foot tapping source. Again, same methodology, but a completely different application. So that was done a few years ago, but then sort of the literature continued to evolve on how can we cope with limited data, and then in came few-shot learning. So a more maybe principled approach on how can we learn from a limited number of labeled examples. And the sort of first such attempt was on prototypical networks, which is now, I think, widely used as a baseline for few-shot learning. The idea is that you, for each class, you have quite a few samples. You have some embeddings of those samples belong to one class, and based on those embeddings, you create a prototype. You can call it a centroid for that particular class. So when a new sample comes in, maybe from a distribution you have not seen before, you would be able to allocate that to the closest possible prototype in that sort of embedding space. And that was also something that we were able to work in the case of, again, on the acoustic scene recognition, that application domain where you would be trying to recognize the acoustic environment of a recording. Limitation of this is that it's a fast approach. It doesn't really require training per se. You just have pre-train your model, but it is limited to single label classification problems, so maybe not that useful. In sounds, we do have potentially taxonomies. We do have also potentially a multi-label classification. We might have many things happening at the same time. That's a very normal thing in general purpose audio. So we try to work a bit more on this. One such approach was on trying to improve on these prototypical networks by trying to introduce some domain knowledge of how sounds are organized in an ontological space. There are quite a lot of taxonomies, perceptual taxonomies of sounds available, and also more commercial tools and datasets like AudioSet, created by Google, for example, does support such a taxonomy. So, for example, if you have a dog barking, you could say that a dog, okay, that's an animal. So you have an animal sort of parent sound as a taxonomy. So we're able to develop prototypical networks that would operate on multiple taxonomical levels. And this is something that could lead to an improvement in making sense of sounds in a case where you have limited data to begin with. And that was something that was presented at the DCASE workshop. DCASE, for those who are not familiar, is the workshop on the detection and classification of acoustic scenes and events. A lot of the research activity in the area of general purpose audio recordings is happening as part of the DCASE community and the DCASE challenge, which is a challenge that runs every year on recognizing acoustic scenes, recognizing sound events, separating general purpose sound events. So it was something that worked quite well in this case. We were able, if we imbued some taxonomical knowledge to sounds, we were able to have some improvement, but still didn't solve the issue that this was still very much a single label classification problem. So further work done in ICASP 2024 in this time, we're able to extend these hierarchical prototypical networks to solve multi-label classification problems. In this case, they converted a multi-label classification problem to multiple single-label tasks. And that was one potential solution. And we followed up on that in the music domain. That was published last year and also presented at ICASP 2025, was on proposed label combination prototypical networks. So in this case, we created new classes. Every time you see a new label combination in a multi-label scenario, let's say you have a dog and a car together, a dog barking at a car horn, for example, then you have a new class. And even that might sort of, you might think that this might lead to a computational explosion because there's very little learning to be done in these sort of prototypical networks. It still scales pretty well. And we were able to use this particular method for multi-label audio classification applied to a global data set of different music cultures. And this is something that worked pretty well, and we are continuing work in this particular area. So this is what I wanted to cover on the first part of the talk, was about sort of machine listening for in limited sort of data scenarios. Maybe if there's any question on this part, I'd be happy to take it now.
So, any questions on this part? I think maybe we could continue, and if there's any question, I will.
Sure. Yeah. And of course, if people would like to ask questions in the chat, then we can follow up later on.
Sure.
So the second sort of part of what I wanted to present today was on multimodal learning for machine listening. I'm sure everyone attending today's meeting would have some sort of acquaintance or even might have worked themselves on multimodal methods. Is something we are seeing quite a lot, particularly in the context of audio plus text. There's more and more use cases, applications of this happening all the time. In music, in the music domain, we are, both the industry and researchers have been working traditionally with tags. So you have a recording, could be 2-3 minutes long, usually something like that, a song. And then you have a series of tags. This is pop, this is rock, this is moody, this is groovy. And this is how people would normally work, but having a longer form description can add a bit more nuance, can add more information, more context. It is also useful if we think about a music production perspective. A lot of producers, they would like to have the functionality of maybe searching through a more sort of open source sort of interface where they might be typing a sentence. I'm looking for a song that might be a bit slow in the beginning, then a bit atmospheric, and then groovy at the end. So this led to some work on creating captions, natural language descriptions of music audio. There has been already quite a lot of activity in this particular task on audio captioning as part of this DK's challenge series, and we were trying to see whether we can adopt a similar sort of approach for the case of music. And this was done in collaboration with Universal Music. The first approach we did was a fairly, I would say, traditional sort of supervised approach. We used a fairly standard sort of convolutional neural network with a long short-term memory network with some temporal intention. And we really treated that as a sort of supervised classification problem. Back then, there were not a lot of captions to begin with. It was a small data set. If I recall correctly, it was about 2,000 pairs of music recordings and corresponding text descriptions. But that was the first attempt. We were also back then investigating how can we combine the two modalities? What is the best way to fuse the information between the two modalities? Should we do that in early fusion or late fusion? In the end, and I think this also corroborates a bit the results that you might be finding in different fields, different application domains, it's not crucial, the point where you fuse the information. What is more crucial is maybe how powerful is your audio encoder versus how powerful is your text encoder. And it does happen that usually the text encoders, given the advances happening in NLP are much more powerful than the audio encoders that we might be having, which leads to issues that we might be describing as modality imbalance issues. So sometimes, which is why sometimes in these sort of audio language sort of multimodal models, you have the some outputs might be a result of hallucination, basically, maybe from the text encoder part, because the audio encoder is not strong enough. So in order to make things work a bit better, we were also sort of invested some time in developing a more general purpose model that would be used for pre-training pairs of music audio recordings with corresponding text descriptors, and then we were able to sort of see if these were useful for a series of downstream tasks. Some of these were traditional tasks in the music information retrieval domain. And by adopting a weekly sort of supervised paradigm that combined pairs of text descriptors and audio, we were able to learn some fundamental sort of music audio representations that were able to be used in quite a few downstream tasks. And one way this was able to work quite well was on trying to co-attend both the audio component to attend the text component and vice versa. Usually, if you think about audio recording and a corresponding text caption, there should be some correspondence between the two, maybe in terms of the structure of the piece, is the structure of the recording. So there should be an element of temporal alignment between the two. And we did investigate quite a few different sort of pre-training paradigms, whether that was mask language model, which is pretty common, mask audio modeling, where we hide some parts of the audio part. In this case, it was a spectrogram, and we hid some parts, some patches, some type frequency patches of the spectrum, and we try to reconstruct them using multimodal information. That worked pretty well. And then following also a clap paradigm, we also created a contrastive approaches for learning multimodal text audio spaces and representations. And these were appeared to work quite well for a series of tasks, and we're also able to adopt also to maybe unseen domains. Having said that, still there are limitations. There's still area for improvements. Back then, we continued to increase our data set, and we were able to have a data set that was now in the order of tens of thousands of pairs of recordings and text pairs. That was good, but still performance, at least using the traditional sort of metrics that people would use to evaluate captioning across different domains. People might have heard of the blue, the rouge, the spice metrics. Was not necessarily high, but didn't mean that the actual performance from a user perspective was poor. So if you see some of the examples we have here, so the ground truth descriptor and the predicted caption, you can see quite a lot of semantic similarities appearing that might not be apparent when using the sort of objective, let's say, NLP metrics that are widely used in the community, which also indicates the need for us to create maybe more suitable metrics for evaluating the predictive performance of audio captioning models. Another issue we had is that even though we had by now accumulated quite a lot of data with help from our industry partner, this data is still not publicly available, unfortunately, due to copyright restrictions. So we did make an effort that was done in collaboration with people from Universitat Pompeu Fabra in Barcelona to create a public, openly available data set that can support music captioning or any other sort of music and text tasks. And this is the song describer dataset. We used an existing source of Creative Commons licensed audio recordings, and we crowdsourced captions. We put it to the community, and we did manage to accumulate a dataset of 1,100 human sort of written natural language descriptions that corresponded to about 700 music recordings, and this is publicly accessible, and has been used so far for evaluation as an evaluation set for the community. And with the advent of additional tasks in the multimodal sort of audio text space. We also did propose a mutual music benchmark. So that was basically a benchmark for music QA, acoustic music QA. So something we can evaluate the performance for audio language models that included more than 1,000 multiple choice questions across 600 music tracks. And that is still something which is quite challenging for machines to pull off in terms of answering quite sort of musically relevant, I would say, musicological questions about the content and the understanding of a music recording. So now I'll move on to the last part of the core sort of part of my presentation, which was about self-supervised methods for machine listening. I assume that many people attending would be familiar with self-supervised methods. I know that a lot of the groundbreaking work that's being done on self-supervision has very much been originated from Mirko's and Pune's group, but for the sake of completeness, I can define self-supervised learning as a special case of unsupervised learning that relies on pretext tasks that exploit some knowledge about the data modality used for training. So basically, we create some proxy tasks for trying to, and basically solve them using supervised learning methods, even though we might not have labels to begin with. Mass prediction is one such case. You can use contrastive tasks, and these have been used quite successfully in audio identification cases. Clustering could be one such case. There has been a lot of work in self-supervised learning, in vision, in speech, of course, less so for music, which was where we came in. We were first trying to see whether existing speech self-supervised models, so models that learn general representations of acoustic of speech audio, will be able to be transferred to the music domain. Data 2vec, Hubert are such speech self-supervised models, and we're trying to see would we use them just as they are for solving music understanding tasks. The answer was maybe. The answer was that it can be useful, but if you are able to pre-train on music, it's better. But in both cases, this particular sort of models that were optimized for speech. In speech, usually you have one speaker, typically, not always, of course, but in many cases, you have one speaker at a time, and maybe you treat the rest as being noise. Or at least you have one target speaker and the rest of the speakers that might be simultaneously speaking, you might be considering them and put them in the other bucket. In music, it's a bit different because we very often have what we call polyphony. So we have many instruments producing musical notes at the same time, and all instruments might be considered to be equally important. And you have overlapping frequencies. You have what might be called harmony, where the instruments might be producing pitches that are not just random, but there's a structure to them in the sense that you like to have pitches that might be what we call harmonically related. So you might have an octave relationship where every second harmonic of the first source overlaps. We like to have overlapping partials in music, and that sort of makes the problem a bit challenging, and maybe these models were not optimized for this music domain. So this is where we came in with MERT, music understanding model with large-scale supervised training that was published at iClear last year. Here we used a multitask methodology to make it work. In the one hand, we used the encodec as a reconstruction gloss, but on the other side, we also had a constant Q transform, which is it's a time frequency representation, which is a bit musically informed. So in a SDFT spectrogram, the y-axis corresponds to linear frequency in hertz. In a MEL spectrogram, the y-axis would correspond to the MEL bins or to the frequency in the MEL scale. CQT spectrogram, the y-axis in this case would correspond to octaves and potentially to things like semitones or sense, which is a subdivision of a semitone. So this is a musical concept. So there's a bit of a musical understanding behind this representation. And this was useful to have as a proxy task. This was very much a self-supervised model for learning a representation that would be useful for solving music understanding problems. We did publish quite a few variants of MERT. We had one variant that used some proprietary music, but we also have a model variant which is trained just on publicly available data that people can use. All these are in Hugging Face. It was nice to see that was community impact for MERT, more than 750,000 downloads in Hugging Face for the model. So that means that people are using that to solve different tasks. MERT does have some capability in handling longer sequences. That's another problem because music, typically you have quite long recordings, could be several minutes long, even tens of minutes long. But still the training context is fixed to 5 seconds, which limits some of the temporal capability that it has. And the good thing about MERT is that we were able to then adopt it to solve some of the tasks that I presented in the first part of my talk. We were able to adapt it to more, let's say, low resource tasks. In this case, we had the problem of playing technique detection. So this is a problem in music. Sometimes you have what we call playing techniques. Could be what we call a glissando, vibrato. There's quite a lot of playing techniques also in other cultures. We had a data set of Chinese music that we used in this case. This is a very much low resource problem. You only have a handful of labeled data that you can use with, but pre-training on MERT and fine-tuning for this particular downstream task was a viable solution. And of course, MERT also was a good case study for going beyond just audio understanding, audio music understanding, by combining MERT encoder with an existing LLM, large language model. You can then use it for some of the multimodal tasks that I presented before, whether that's about audio captioning, audio Q&A. In this case, we used the Vicuna language model to come up with MusicLingo, a system for that did music captioning, but also did music Q&A and similar tasks such as text-based audio retrieval. So that was the all the core content I wanted to present, but looking ahead, what is happening and what could be happening in the field. We are still seeing, despite all this progress that has been done in language models, audio language models, multimodal AI, still the more traditional, I would say, acoustic only models dedicated to solving a particular task are still working better compared to maybe the multimodal models, at least in the domains that I presented before in music and everyday audio. Another issue is, of course, environmental constraints or also even resource energy constraints. It's very hard to train models from scratch in this case, or pre-train models from scratch, and whether it's possible to do continual learning for models. So instead of having a model that you need to retrain once a month, that might take several weeks to retrain to begin with, can we actually continuously update those models? Then the other issue is that, of course, we are relying a lot on developments from NLP. We are relying a lot on developments from computer vision too. We are sometimes constrained a bit by the newly emerging audio plus text paradigm. And sometimes we might be missing on other modalities that might exist. If I think about music, sometimes you have music videos. Why not make use of the video signal? When I think about music, we also have what we call a score, a musical score. This is something which is quite unique to this domain. It's basically a symbolic representation. Some people might be calling this a language. It might be debatable to call it a language, but it's definitely a symbolic representation that is not maybe fully used as of yet. And of course, you also have even images of such scores. So you can also go back to the visual domain. So maybe we can think about multimodal models that might go beyond just audio and text. And again, because of the data proliferation around maybe what we might be calling high resource domains. In the same way that in speech you have high resource languages, you might be having lots of corpora in English, Mandarin, but there are other low resource languages out there. In the same way, we have low resource music styles, we have low resource music cultures. And there's also low resource environmental data, whether that's about particular animal species, whether it's about particular acoustic domains, domestic domains, that we might need to think about how to enable these big pre-trained models to rapidly adapt to an unseen low resource scenario. And again, resource efficiency, sustainability is a constant issue, and whether we should be moving towards more lightweight and maybe sustainable practices when developing our multimodal approaches, which can take significant amount of computational resources to pull off. And that was the talk of today. Thank you for attending. Of course, this work was not just was a collaborative work. Many people were involved in order to produce that over the years as part of the Center for Digital Music, as part of Queen Mary. Thank you very much for attending, and I'd be happy to take any questions you might have.
Thanks a lot for the great presentation. I think we have a couple of questions, so maybe I will start from chat. So I think it related mostly to the first part. How can hierarchical reasoning improve the reliability and interpretability of sound event recognition under ambiguous or noisy condition? In particular, can hierarchical prototype provide a structured confidence estimate? For example, assigning high confidence to higher level categories while maintaining uncertainty across finer grained classes like dog vs cat.
Thank you. That's a good question. Yet the current model does support this sort of uncertainty. So it basically would promote maybe if you have, let's say, a dog sound, it might promote that this is coming from an animal parent class, but does not necessarily impose that this would be the particular branch. So it would give it maybe a bit of a boost and a higher confidence. Issue, however, still is, I think, on the fact that there's no clean-cut taxonomy of sounds, and sometimes you might have sibling sort of child classes of sounds that might appear in different branches of your tree. It might be better to think of sounds taxonomies not being as a tree-like structure, but more of a sort of a graph, an undirected graph, as opposed to a more clean-cut sort of tree-like structure. And I think this is where the challenge lies, and also to link up better with existing work that is being done in music perception, audio perception, acoustic cognition, and so on, to make use of existing body of work in creating those sound taxonomies.
Okay, perfect. So I think, Sam, do you want to ask your question?
Yes, thanks, Emmanuel, for the great presentation. I wanted to ask you about the audio language models. You mentioned that there is still a performance gap between like the regular deep learning models and audio language models. I was wondering, like, yeah, like then why should we pursue this? Like, why do you think this is like a good idea?
Yeah, that's an excellent question, I think. So we did like in, I don't know if you're familiar with you are definitely familiar yourself on the Izmir conference. So the Izmir conference is the annual conference of the International Society of Music Information Retrieval. We had a paper published just a couple of months ago called the CMI bench, where we put to the test all these new audio language models to traditional tasks. And the performance was, I would say, quite poor of the recent sort of audio language models. There's the question, why should we continue to proceed with this? I think one reason for continuing to move forward with this is because we can unlock new applications that we were not able to solve before. Audio captioning is one of them. Text-based audio retrieval is one of them. Audio Q&A. These are all new tasks that we cannot really solve with more constrained audio-only models. And this is, I think, one area where audio language models can have a big factor in. I am still not fully convinced that audio language models, multimodal models, are still the optimal way to tackle a specific audio understanding task. Also, from a production perspective, it might be just more efficient computationally to rely on a more dedicated, smaller model that will be just focused on a particular task.
Yes, yes, yes. Yeah, thank you. And I have another question. You also mentioned like continual learning as another like potential possible direction. I was wondering like if you had more details about that, like what in particular could be in what context, like like more technical
Yep.
details about that. Yeah.
Yeah, absolutely. So I have been doing some work recently on incremental learning. This is something that has happened also in discussions with industry partners. Sometimes, if you think about, let's say, record label, they have a set of tags. Then the next year, there's new trends coming in, new styles, new tags appear. What do you do there? You have millions of recordings already used to train your audio tagger? Do you retrain everything from scratch? This is potentially very costly. So this is where we started sort of investigating into incremental learning methods where we can maybe update the set of classes we might be able to support, update also the domains that we might be able to support.
Mhm.
And again, I think this is something which is useful not only from a theoretical perspective, but there's a very practical reason for
Yeah.
doing this for computational purposes.
Like class incremental learning setup.
Yep, exactly.
Okay. Okay. I see. Thank you.
Okay.
Okay.
There's also, yeah, class and task incremental learning, I would say, is also another
I
reason.
see.
Yeah.
Okay. Okay.
Okay, maybe I also have one follow-up question on audio language models. So you said that there's a gap, and I have seen that in many of these audio language model, the performance is very dependent on the input that you pass. And most of them use something like Whisper, Vavellem, or in some cases also Beats. Have you tried to also adopt this audio language model with the MERT representation and see maybe it could narrow down the gap that you have seen or not? Or if there's any, you are aware of any other work that doing that.
Yeah, thanks. So, I mean, there's a lot of work and there's a lot of models out there. I mean, right now, I think QN audio, for example, is pretty good as a general purpose sort of audio language model as well that works pretty well on music too. So I think that might be one of the sort of best models out there for music. We have tried Whisper, also for singing only tasks. We had some projects which are about lyrics transcription, which is equivalent to speech recognition, but for the music sort of domain. I think what I've seen is that existing models, that includes MERT, that includes Q1 and a few others, they are quite good in solving, I would say, high-level tasks that might be about clip-level classification, for instance. They might be quite good in solving tasks that are about the source mainstream domain, high resource domain that have been pre-trained on. They are, however, less successful in handling tasks which are a bit more fine-grained, for example, source separation or pitch detection, where your prediction is really at the sample level or maybe at a 10 millisecond sort of hop size. They might be less successful in adopting to unseen low resource domains, and I think there is a need for more fundamental research in that area.
I see. And have you tried something like MERT representation for most of like a generative music task, like generating music or something, and see what's the performance? Because we have seen that in a speech, Vavellem or at least K-means on
Yep.
Vavellem have a very
Yeah,
good
absolutely.
performance. So
Yeah, we had I didn't include that in the presentation. We have an MUPT, which is a generative symbolic music pre-trained model. The good thing about symbolic music is that it's a bit closer to natural language, and it's a bit easier to generate music in the symbolic domain. And you will see that most of the generative work done in music is done at the score level as opposed to the audio level. It's just much easier to generate something which is in terms of a list of notes, let's say, as opposed to audio samples, which is much more challenging. This is definitely an area for growth. And again, I think sometimes one challenge I'm seeing in my community at least is that sometimes we are relying a bit too much on what is being done maybe in NLP, or we are relying a bit too much on what is happening in computer vision. But some of the challenges we have are a bit unique to our domain. I mentioned polyphony and harmony as some of these. So I think there needs to be more work, fundamental work, to address this particular domain that we have been working on in order to really address sort of generative tasks.
I see. Perfect. Thank you. Mirko, do you want to go?
Yeah, that's very quick because you already partially replied to that. But I would like to go back to this like audio LLM, multimodal LLM, because in speech we are seeing that there's like multimodal LLMs are eating pretty much everything, meaning that you won't have any more a model for speech recognition, a model for speech separation, a model for any other task, but everything is included, absorbed by a single multimodal LLM. So I know you were a little bit skeptical, like in the previous replies, but do you think that in the long term, in the end, like this will be the final approach, right? Having a big model doing everything, or you still see room for task-specific models?
Thanks. I think that's a great question. I think it's still, a matter of debate, let's say. I could think that in a production context, in a real world production user-facing application, there's definitely an argument to continue focusing on smaller task-focused models that might be focusing also on a limited set of modalities. Having said that, there's definitely an argument for continuing research on, and you could call it omni-modality models. There's a lot of research on that sort of aspect nowadays. That might be in the end distilled to a particular task further down the line. So I think maybe one sort of potential direction I could see is on continuing to work on a general purpose omni model that you might be able to distill in the end to your particular subset of modalities that you might be interested in and the particular subset of tasks that you might be interested in.
Yeah, that I agree on that. Thank you.
Perfect. Arjun, do you want to ask your question?
Yeah. Thank you for the talk, Emmanuel. My question is around how usually multimodal LLMs focus more on the text because that signal is strong. You mentioned early fusion, late fusion as one method. We can maybe make that balance equal. Are there other methods in multimodal LLMs or for cross-modal adaptation that
Thank you. Thanks, Arjun. So my former PhD student, Ilaria Manco, worked a lot on trying to address the modality imbalance issue between the acoustic sort of domain and the audio domain and the text domain. We did try quite a few different approaches, and I always felt that there was a ceiling that we were not able to surpass, and still the language modality sort of was able to surpass the audio, the acoustic modality. In the end, I think one reason is because there's so much research being done on the NLP side of things and comparatively less so on the audio side, is that our acoustic models are just not as strong enough. My suggestion is that we need to devote more efforts, more energy on developing stronger, more general purpose audio encoders, acoustic models, in order to really address the modality imbalance issue. That involves both on efforts on data collection, that involves efforts also on having a wider coverage of possible tasks that you could use for pre-training. I think some of the tasks that we are using so far for pre-training for self-supervision might be a bit too simplistic for learning meaningful acoustic representations. And I think there needs to be a bit more energy from the audio community in order to catch up with what is happening in the NLP domain.
Gotcha. Thanks.
Okay, perfect. I think we're done with all the questions. Thanks a lot. It was a great presentation. Next week, we have Simone Scardopain from University of Rome talking about efficient and resource-constrained dynamic neural network. Thank you everyone for joining and looking forward to meeting you next week.